Hey there, in this video we're going to look at a process called rationalizing the denominator, which is something that you can use when you're working with fractions that have radical expressions in them. So rationalizing the denominator is the process of taking a fraction that looks like that has an irrational number, a radical on the bottom, and turning it into an equivalent fraction that has a rational number on the bottom. Now you're going to be rewriting it in another form, not changing the value of the thing. Much like you would take a fraction like 3/4, multiply the top and the bottom by 2 and you'd get 6/8. You've created a new fraction that has the same value, just different terms on the top and the bottom. To take this first one and rationalize the denominator, as long as we multiply the top and the bottom by the same thing, we won't change the value of it. And the number that's easiest to choose to turn this denominator into a rational number is multiply it by √3 over √3. If you do that, √3 times √3 on the bottom just gives you 3. On the top, all you have is 5 times √3. So this original fraction, 5 divided by √3, is the same as 5 times √3 over 3. Again, you haven't changed the value, you've just rewritten it in different terms where the denominator is now a rational number. Second one here, if we want to turn that into something with a rational denominator, we look at what's in the denominator now. This is the part you have to focus on here. You can multiply by √7 on the bottom, √7 on top. You're multiplying by something that equals 1, so again, you're not changing the value of it. But what we're going to end up with here is, on the bottom, just 2 times √7 times √7 gives you 7. And on the top, √11 times √7 is going to give you √77. And then you can write the bottom as 14. So you have √77 over 14. That fraction is equivalent to what we started with. It's just got a rational number on the bottom. Third one over here involves cube roots, so we have to think a little bit about what we're going to multiply by. The denominator here involves cube root of 5x. What we're going to multiply by here on the bottom is enough to make this into a perfect cube. Over here we chose √7 because we had a √7, and √7 times √7 is 7. This is because this is square roots, the index is 2. Over here we have cube roots, the index is 3. So we actually need to multiply a couple times by cube root of 5x. So the simplest way to write it here is realize that I need to have 3 of these things underneath my radical sign when all is said and done here. So what I'm going to multiply by is, I can either write cube root of 5x times 5x, or I could write cube root of 25x squared, whatever you prefer. But that's what I'm going to multiply by, because on the bottom now I have, well, we'll leave the 10 out there for now, and we're going to write this as cube root of 5x times 25x squared is 125x cubed. I chose that because now I've got both of those things are perfect cubes. On the top I have 11 times cube root of 3 times 25x squared, or in other words, 75x squared. The bottom I'm going to simplify a little bit there, which is the point of this. On the bottom I have my 10, and I have cube root of 125x cubed, which is 5x. That was what I did. It's what I started with here. And then to write it in my final form, I'm going to leave it in. I've got 11 cube root of 75x squared over 50x. That's equivalent to what I started with a rational denominator. Right? Now we're going to look at some expressions that have 2 terms in the denominator, and we're going to see a difference in what we can do, what we need to do there to rationalize those types of fractions. Now your first instinct looking at this first one here might be that you focus in on that root 3 and think, okay, I need to multiply by root 3 over root 3 because then I'm going to end up with just a 3. The problem is if there's two terms on the bottom here, I need to multiply this by both of those terms. And yes, the root 3 times the root 3 would give me root 9 or 3, but the first term here is going to be root 3 times 5. It's going to be 5 root 3. So there's still going to be an irrational number on the bottom. Now, there's a little trick I'm going to show you here to fully make the radicals disappear from the denominator, and is to multiply by something called the conjugate of what's on the bottom there, of that binomial. The conjugate of a binomial like that is the same terms, but the opposite sign in the middle. So the second term has the opposite sign. If this is 5 plus root 3, the conjugate is 5 minus root 3. If this were 5 minus root 3, the conjugate would be 5 plus root 3. All right, now you'll see why that is going to work in a second here. We'll multiply out these two. Now remember, you're multiplying some binomials there, so 5 times 5 is 25. And we have 5 times minus root 3. 5 times minus root 3 minus 5 root 3. Then we have 5 times plus root 3 plus 5 root 3. And then we have our last term here, minus root 9 or 3. Now the reason that's going to work is, if you notice here, you have plus 5 root 3 minus 5 root 3. The two middle terms there actually are going to cancel each other out. So all you're going to have in that denominator is 25 minus 3, or in other words, just 22, which is a rational number. No root signs, no radicals involved anymore. On the top then, since I didn't do that yet, we're going to multiply that 4 root 2 times each of those terms and see what we have. So we have, first of all here, 4 root 2 times 5 is 20 root 2. And we have 4 root 2 times root 3 is going to be 4 root 6. So we have 20 root 2 minus 4 root 6. We have 20 root 2 minus 4 root 6 there. And this is a fraction that now has no radical in the bottom. So it's got a rational denominator. Now there is one more thing you can do here if you look carefully at it. Each of these terms has an even coefficient. They all have a common factor there. So what we can do is we can reduce it a little bit by dividing out the common factor. If all of those terms, there's 3 terms in the whole thing, this, this, and this. If all of those terms can be divided by the same number, we can reduce it. They can all be divided by 2. So we can instead make this 10 root 2 minus 2 root 6 over 11. That's the simplest form of that fraction with the denominator being a rational number. All right? Let's look at that second one. To rationalize this one, you look at that denominator, 3 minus root 5. So we're going to multiply by the conjugate, 3 plus root 5. And of course you have to make it the same on the top here, because multiplying by 1 doesn't change it. On the bottom, we can make this a little bit more efficient here. If we recognize that the middle terms are going to cancel out, then we don't even need to put them down. We can just know that 3 times 3 is going to give us 9. We can just think to ourselves, 3 times that, root 5 is plus 3 root 5 minus 3 root 5. They cancel out. And then the last term is going to be minus root 25, or just minus 5. Don't even bother putting those other two terms down there. On the top, we have 2 binomials as well. Now these are different, so there's the middle terms. We've got to write all 4 terms here. We have 12. We have plus 4 root 5. We have plus 3 root 5. And we have lastly there plus root 25, or just plus 5. If we simplify that, the bottom's easy to simplify. It's a 4. The top, we have some terms that are alike there. The 12 and the 5 we can put together as 17. And the 4 root 5 and the 3 root 5 we can put together as 7 root 5. That expression is equivalent to the original one. It just has rational denominator. As always, you can check on a calculator, carefully put that in and work out its decimal value, and carefully put that in and work out its decimal value, and you'll find that they are the same. This one we don't have to reduce like the one before because there's no common factor in those coefficients that are involved there. Let's look at the last one over here. That last one, again, you're looking at the bottom, not the top. It's always the bottom. The denominator is what you're trying to rationalize. So we're going to multiply by the conjugate of that expression we have there. 3 root 2 minus 2 root 6. Same terms, opposite sign in the middle. And on the top, 3 root 2 minus 2 root 6. If we multiply it out, again, let's not worry about the middle terms. We'll just think them. We won't write them down. First term is going to be 3 root 2 times 3 root 2. Or in other words, 9 times root 4, or 2. That's the first term. The middle terms, minus 6 root 12, and then plus 6 root 12, right? Because the 2 times the 3 is 6, and the 6 times the 2 in there is 12. But we're not going to bother writing those down because they're going to cancel each other out. We are going to write down the last term. 2 root 6 times minus 2 root 6 is minus 4 times root 36, or just 6. On the top, we need to multiply out this times each of those other two terms. Root 6 times 3 root 2 is 3 root 12. And then root 6 times this one over here times 2 root 6 is minus 2 root 36, or just 6. Now we'll simplify each part of that. The 2 times 6 over here we're going to write as 12. On the bottom we have 18 minus 24. The 3 root 12 here we're actually going to simplify because root 12 itself can be simplified. Root 12 you can write as root 4 times 3, which of course you can write as 2 root 3. And then with my original 3 that I had there, I'll put that one in. So now what we have here is we have 6 root 3 minus 12, and on the bottom here we have 18 minus 24, which is negative 6. Now we can do similar to what we did in this one over here with noticing that all of these have a common factor. In fact, not only do they have a common factor, we can just think of this as dividing each term separately. This we can divide because the coefficients divide nicely. 6 root 3 divided by minus 6 is just going to be minus 1 root 3, or in other words, minus root 3. And then minus 12 divided by minus 6 is just plus 2. So that expression is equivalent to the one we started with. And if this leading negative sign bothers you, there's nothing wrong with writing it in the reverse order. And instead of saying minus root 3 plus 2, you can say plus 2 minus root 3. Either one of those is fine. Right? So that's rationalizing the denominator of fractions that involve radical expressions.